So for temperature, let us simply write down temperature is the average kinetic energy of the particles in a substance. Temperature is measure of the average kinetic energy of the molecules of a substance.
Okay. Average kinetic energy. Okay.
Okay, so for energy, we know that there are two main types of energies. One is what we call PE, potential energy,
Mm-hmm.
and the other is what we call KE, kinetic energy.
Mm-hmm.
Okay, PE or potential energy is the energy that any particle or any body possesses by virtue of its position,
Mm-hmm.
right? And kinetic energy is is the energy which a particle has because of its motion.
Mm-hmm.
Okay. Um. Okay. So what's the uh. Okay. So is kinetic energy what other types of for any given particle, it's not that
Mm-hmm.
for any given substance, it's not that it's particles they have just the kinetic energy, they'll also have potential energy. So temperature or heat is just one property of a substance. It is
Mm-hmm.
not representative of all the energy that is there in the particle. So
Mm-hmm.
another related concept which a student might confuse this heat energy with is internal energy. So the internal energy, let's write the definition for that down as well.
Okay.
And hopefully, if you don't understand anything, you'll write then and there ask me to repeat, because all the
Mm-hmm.
concepts that we're talking about, we'll be using them again later on. So
Mm-hmm.
better get things clarified the first time I mention them, so that when I later build on that concept, you're able to understand that as well, and then do not have to repeat the whole explanation again. Okay. The energy of a substance due to the random motion uh, and the potential energy that okay, so we write it as the energy of a, did you just rejoin or did I rejoin the meeting?
Mm-hmm.
One of us did. Okay. Okay, to the to both random.
What's after substance? The energy of a substance
Due to the
due
due
to
to both the random motion of its particles.
okay, due to the random motion. Motion. Mhm. Wait, I'm trying to understand the definition.
Just write it down. I'll explain it again.
Okay, I wrote it down.
Okay. So for any given particle, for any given substance, we said that its particles would have energy.
Okay.
The total sum of all the energies that those particles would have, that would be the internal energy, whether that is Ke or whether that is Pe.
Okay.
Particles would have both Pe and Ke. However, the heat energy or the temperature of the substance, it's just by virtue of the motion of the particles or the average kinetic energy.
Mm-hmm.
The potential energy of the particles, it would result in other properties of the substance.
Mm-hmm.
Okay, the energy within the particles, it results in a substance having some qualities.
Okay.
So the kinetic energy of the particles, it results in the temperature of the substance,
Mm-hmm.
whether it's hot or cold, as you said. But when we calculate the temperature, we are very precise about how hot or how cold something is, and it's something objective. It can be
Okay.
it's not subjective, that for you temperature is something different and for me temperature is something different. That's
Mm-hmm.
for hotness or coldness, that's for heat or how. Okay, for example, this thing of how hot or how cold something is, that is subjective, but the
Okay.
actual temperature of the substance itself, that is objective. That does not vary from person to person. We'll both have to agree that temperature is the same thing. Did you get this thing?
Yeah.
For example, if my hands are cold, I would feel a coffee cup more hot as compared to if my hands were warm,
Mm-hmm.
because the temperature difference isn't as much. When the temperature difference is a lot, we feel the heat or the coldness of the object more. However,
Yeah.
temperature of that particular substance is constant. It does not vary from person to person. Okay. This, then the next thing that we have, mm, okay, okay. There is this concept of delta. Hopefully, you're aware of it. So, for example, if I've got two readings in the initial few classes, I'd be going over a few basic things as well, which you might have covered earlier on. But just
Mm-hmm.
to get things out of our way, so that we know that we have discussed it at least once in our class as well. So, we are
Okay.
using this term delta often. So, for example, when I say delta U or I say delta X, so this delta, it means change.
Okay.
Okay, and
Delta
usually
U means change in
u,
internal energy.
no, delta U is change in variable u,
Oh.
whatever that variable be. Delta X is change in variable X, whatever that variable is. And
Oh.
for change, I take the later quantity, which is usually termed as u2
Mm-hmm.
minus u1,
Mm-hmm.
u2 minus u1, or it
Um.
could be u f final minus u initial, ui.
Mm-hmm.
So, just to, I mean, make you familiar with the terminology, you must have been using this terminology for other things as well.
Mm.
For
Oh.
example, when you calculated change in velocity,
Uh-huh.
you must, did you do ever questions of change in velocity, those velocity equations, v squared is equal to u squared plus 2as, or s is equal to
Yeah,
vt plus
I
half
think
vt
so.
squared?
Yeah.
So, in those questions, we have initial velocity and final velocity.
Mm-hmm.
So, if an object had an initial velocity, let's say ui or vi, and it had a final velocity vf, then in
Okay.
order to calculate the change in velocity, I have to subtract initial velocity from the final one.
Mm-hmm.
That would give me change in velocity. In temperature, we'll see change in temperature of substances. So how much is the change in temperature? Later temperature minus initial temperature is the change in temperature. Simple.
Hmm.
Later temperature minus initial. So for temperature, we use both delta t, or more often we use delta theta. Okay, so
Mm-hmm.
delta theta would be calculated as theta 2 minus theta 1.
Okay.
So
So
theta,
so
theta
it's final minus initial.
final minus initial or later minus initial.
Okay.
Okay, this. Okay. Then the next thing that we have is what we call thermal equilibrium.
Hmm.
So thermal
Can I
equilibrium is
tell you what I know about it?
sure, sure, go ahead.
Okay, I don't know if this is correct,
Hmm,
but I think when two objects meet, their temperature, there's a point when it becomes the same.
hmm, hmm, hmm. That
Their
is what thermal equilibrium is, that the two bodies that are in physical contact with each other, they have identical temperatures. That is precisely how we define thermal equilibrium. But since we are
Okay.
noting everything important down, let's note this thing down as well. And we will note this down, and I'll tell you one more reason why we are, even bothered with this concept in the first place.
Okay.
Okay. Uh, Thermal equilibrium. By the way, towards the end of the class, remind me to take a stock of all that you have covered in both the subjects. When is the exam date? And let's set a roadmap of how much topics do we have to cover, how much classes do we have in between, and how do we divide the syllabus then?
Hmm. I'm not sure for math how much is coming,
Hmm.
but last time we had 7 lessons.
Mhm, mhm.
So for physics, I know it's just this chapter only. Heat.
Chapter 9. Hmm.
Yeah, that's it.
So the two bodies, they have to be in physical contact, two bodies in physical contact with each other have identical temperature. With each other have identical temperatures.
Okay.
Okay. Uh, if we want to take readings of temperature, temperature is only meaningful when the object is stable or when it has thermal equilibrium.
Okay.
Okay, so for an object to for an object, for example, to note a particular reading and then to conclude something from it and then to make observations about it, the object has to be in such a state that the bodies, all the bodies that are in contact with each other, they have the same temperature. If they do not have the same temperature, then their temperatures would keep on changing. The hot body would keep on passing its higher energy to, for energy, for heat energy, we know that it spreads from an area of higher concentration to an area of lower concentration, meaning that if I put two bodies together, one is hot, more hot than the other, so the
Yeah.
body which is more hot, it would pass on its energy to the other body.
Hmm.
Okay.
Heat goes from down to up, right? And cold air goes from
The
up
hot
to
air,
down.
I'll tell you the reason for that as well when I mention the second point. Right now what we need to know is that heat travels. Okay.
Hmm.
And heat travels from area of higher concentration to area of lower concentration.
Because of density.
uh because that is how energy works.
Okay.
Because that is how energy works, whenever there is an energy, uh, uh,
But cold air is denser, right?
cold air is denser, and I'll give you reason for that in a bit.
Okay.
Okay. So another proof of what I'm saying, that heat, it travels from area of higher concentration to area of lower concentration. If I
Hmm.
put hot water
Okay.
in a mug, the
Okay.
hot water, it would pass on some of its heat to the mug. right?
Oh, yeah.
Okay, I mean, simple observation, but maybe we didn't ever put it
It's
in words.
it's transferring its heat.
Hmm. The other important thing to know over here, or the other conclusion that I can draw from this thing, is that there is a thing called heat, but
Mm-hmm.
there is in itself not a thing called coldness. Coldness is merely absence of heat.
Oh,
So heat exists as a substance, heat exists as a property. Coldness does
mhm.
not exist as a property.
It's not a property.
I mean, it's simply absence of heat.
Okay.
How cold something is simply how much it lacks heat. Heat is
Yeah.
again coming back, going back to the definition of temperature. Temperature is the average kinetic energy of the molecules of a body. If
Mm-hmm.
that average kinetic energy is very high, the object will be hot. If that kinetic energy is low, the object would be cold.
Yes.
Okay. The other property maybe we should talk about is, hmm, okay. So the other property is matter expands as temperature increases. So,
Thermal expansion.
hmm, matter expands.
I should write this down, right?
Yes, please. As temperature increases. For the first one, above thermal equilibrium, if you could give the, is there some space on your notebook? Did you leave a line or something? Temperature is meaningful only when it is stable.
Okay.
Temperature is meaningful only when it is stable. Okay.
Okay, I wrote it.
Hmm. The next thing that I mentioned is that matter expands as temperature increases, and
Mm-hmm.
what you say is called thermal expansion.
Thermal expansion.
Um, why does it expand when temperature increases? So let's say
The
this.
molecules,
Hmm, hmm, the
like when it gets heated, the molecules move faster.
Very good. The molecules, they move faster. They try to, I mean, in case of solid, they'd vibrate more into each other. In case
Okay.
of liquid and gases, they'll move faster, so they'll move
Mhm.
farther away.
Yeah. In
Okay,
solids, the molecules are packed, right?
they are packed together. Yes.
Okay.
Okay, so that would result in, I mean, when they vibrate against each other, they'll move slightly apart. What
Okay.
that results in is lowering density. So we say density
Mhm.
is equal to mass per unit volume. So when we
Okay.
increase the temperature, when we increase the temperature,
Hmm.
mass stays the same. Since
Okay.
they are vibrating more vigorously, they move farther apart, so
Hmm.
volume increases. And
Okay.
when denominator increases, this whole value of density would decrease, right?
Hmm. Yeah.
That is why hot air is less dense, and as it
Um,
loses density, its weight,
mhm.
I mean, it then goes up.
So when something is heated, it gets denser or like less dense?
Less dense.
Less dense.
Hmm.
Okay. Sorry, I just wanted to know.
It's fine, it's fine. Okay, so it becomes less dense, and for denser objects, we know that if I put an object whose relative density is more than that of water, it would sink to the floor of water, or it would sink in
Yeah.
the water. And any fluid, if one object is put in another fluid, as its density decreases, I mean, if its density is less than that of the fluid, it would go up,
Hmm.
and if it's more than that of fluid, it would stay down. So for air
Yeah.
within the fluid, or within the fluid, for example, liquid or air, if
Hmm.
air it becomes less dense, that less dense air would go up, and more
Hmm.
dense air it would come down.
Yeah.
That is why hot air balloon it lifts up. It's
Yeah.
using the same
Just
principle. Hmm,
just like gold sinks because its density is more than water.
hmm, hmm, hmm.
That's why, right?
That's why an iron nail it sinks in water, but a ship does not.
Because a ship doesn't sink.
Do ships sink?
No. Wait, but but
Did you ever think that ships are also made of steel, right?
but sinks, aren't they more denser than water?
Nails? Ships? Ships are not
Wait,
denser.
now.
They use this concept. This is called relative density. So anything which is more dense than water would sink. For ships, they spread that mass over large volume.
So it
Agreed
doesn't sink.
mass, so it doesn't sink. The other reason is, again, we would study perhaps this more in area of when we study density. There is a thing called
Uh-huh.
water of displacement. Whenever I put
Okay.
anything in water, it would displace
Okay.
some water. For example, a glass filled with water, if I dip any object in it, some water it would fall off the edge of the water, edge of the glass, right?
Okay. Yeah.
That water that falls off the edge of the glass, it's called water of displacement. So any
Oh.
object when it's put in water, it displaces some water because it has got a
Mhm.
volume, and it, since it needs to
Mhm.
be there in the
Yeah.
liquid itself, so it have some volume of liquid go away. So the
Yeah.
volume of the liquid that goes away, if its mass is more than the mass of the object,
Hmm.
then the object will float. If the object's mass is more than the mass of this water of displacement, then the
Hmm.
object will sink. So these are
When
the
when the buoyant force is balanced,
hmm,
the
hmm,
object will float, right?
hmm, hmm,
Okay.
hmm. And when is the buoyant force balanced? We'll see.
When
We'll study that in more detail when we get to that topic. Okay. Okay. Um.
so basically, behind ships, there's like physics, right, to make
Hmm,
it
hmm,
float.
hmm,
There's like a science
hmm,
behind it.
hmm,
Okay.
hmm. True. True. It wasn't a random incident that some ship got made and it started floating on water, and we were like,
Okay.
"Yay,
But
good
if there
luck."
was no science behind it, it will sink, right?
If there was no science behind it, it could sink. I mean,
Okay.
sometimes we are lucky as well. Science, a lot of times, not, I don't know, a lot or sometimes, but science at times it discovered as a matter of luck.
Oh,
So just we
yeah.
happen to observe something happening, and we note down the observation and we study it, and then we know the reason behind it. But for example, all these people who have been using boats, ask any fisherman, does he know the science why his boat floats? He wouldn't.
He wouldn't know.
Hmm. So all you need to know is what works and what doesn't work. And if you want to
Okay.
study physics further, or if you want to become a doctor, then perhaps you need to know why these things work.
Oh God.
Okay. Another thing with regards to expansion of substances when mm, okay, so for any substance, when temperature decreases, it must contract,
Mhm.
right?
Yes.
Uh, have you ever put a container filled with water in deep freezer or freezer?
Yes.
Why is there an upward bulge on the ice when the water freezes?
On the surface.
I mean, it's like stable water still, right?
Yeah.
When it
Yeah.
freezes, it should have that smooth surface at the top.
Mm-hmm.
But you must have noticed that ice, the top of it, it has a sort of upward bulge. It's not like plain smooth
Mm-hmm.
horizontal. Why is that?
I don't know.
Water, it has a unique property which is called anomalous expansion of water.
Uh,
Okay, so
I don't know what that means.
when temperature of water it falls
Mm-hmm.
below 4 degrees cent until the temperature of water is falling up till I mean from, let's say, 20 degree 10 degrees to 4 degrees centigrade,
Mm-hmm.
water it contracts. But when it declines from 4 degrees to 0 degrees centigrade, it starts expanding.
So ice floats in water.
uh, ice floats in water for the reason that yes, its volume increases.
Okay.
For this particular reason, floats in water, because when that temperature is decreasing, its volume. Okay, see over here. So if I draw this graph, and where do I put temperature over here and volume over here?
Hmm.
When temperature decreases, volume also decreases. Okay,
Okay.
this happens until
You need to
4.
move your screen more down.
All right, it happens until 4 degrees centigrade.
Okay.
4 degrees centigrade. Below 4 degrees centigrade, from 4 degrees centigrade to 0 degrees centigrade, it expands.
Yes.
Okay, it,
Because
it should have continued to contract, but it does not. It expands. And then after reaching, uh, I think usually the books, they say after 0 degrees centigrade it starts contracting again. But the thing is that water, what is the freezing temperature of water?
wait,
Your book would say 0 degrees centigrade, and most of the books it would say 4 degrees centigrade. It's actually
uh,
minus 4 degrees most of the books would say 0 degrees centigrade, right?
it says
0 degrees centigrade.
volume of water increases with decreasing temperature range between 0 and 4 degrees Celsius.
This volume of water, it works.
Volume of water increases
See,
with decreasing temperature
so
range.
temperature is
Between.
decreasing 4 to 0, and the
Uh-huh.
volume of water is increasing.
Yes,
All right. So
I
this is
understand.
the thing. The thing I want to say, I think what happens is that until minus 4 degrees centigrade, until minus 4 degrees centigrade, it keeps on increasing, and after minus 4 degrees centigrade, it decreases. That's what I remember. But the books, they usually say it starts decreasing from 0 degrees centigrade, the
Yeah.
volume. So we'll use that. What the books say.
Okay.
What I want to give you, I mean, just another tidbit over here. What's the freezing point of water? At which temperature does the water freeze?
Mine is.
The books would say 0 degrees centigrade. It actually
Oh,
happens at minus 4. And at
minus
which
4.
point the water melts, the ice melts?
That's the freezing point?
That's the freezing point, right? So actual
Okay.
freezing point is over here, and actual melting point is over here.
Mm-hmm.
This is something strange with water. For other substances, it's the same freezing and melting point. For example, for something, let's say melting point is 15 degrees centigrade. Let's assume. So 15 is freezing and 15 is melting. You decrease it below 15, it freezes. You
Okay.
increase it above 15, it melts.
Yeah.
For water, it's strange. It freezes at minus 4 and it
Uh-huh.
melts at positive 4.
What?
Okay, that is why we usually take this 0 degrees centigrade as
Wait, so
the
what's the neutral temperature for water? What's like the room temperature?
the room temperature would be the temperature of the room, 28 degrees
What?
centigrade.
So,
The room
oh,
temperature
okay.
means 28 degrees centigrade. If you're saying room temperature for water, that would be it.
28.
Room temperature for water, am I getting your question? I mean, room temperature is 28 degrees centigrade. If that happens to be for water, yes. Room temperature for water, let me quickly check.
Okay.
Of water,
It's 20 degrees Celsius.
68 Fahrenheit. Oh my, what's 68 Fahrenheit? And
20 degrees Celsius.
hmm, 25 degrees Celsius.
Oh, okay.
Room temperature is about 25 degrees Celsius.
Mm-hmm.
So, um, if that's the room temperature and that's the room, for everything, room temperature would be that. Is that what you're saying?
Yeah, I just want to know like when water is like not cold or
Uh,
hot.
Hmm,
Like,
hmm.
what is it?
The thing is, what I'm trying to make, it would be 25. It would be the temperature of the
Okay.
room. The thing is that if water had a
Oh.
temperature higher than 25 degrees centigrade, what we
Mhm.
just learned, it would pass off this energy to the room.
Oh.
The temperature of the room won't rise as much because it's
Mhm.
like such huge space, but it would
Mhm.
pass off the energy to the room until it's in thermal equilibrium again.
Mhm. So the water is the same temperature as the room.
Any substance lying in the room, it would eventually come to
Oh.
the same temperature as the place it's lying in.
Why is that? Because
Why is that?
thermal.
Because, all right, temperature is because of kinetic energy.
Okay.
All right, when uh,
So
when something is hot, you leave your laptop, like a very hot laptop, you leave it on desk, its temperature would cool down, right?
yeah.
You leave a hot cup of water on
Yes.
temperature, I mean in room, its temperature would cool down. You
Hmm.
leave ice cream in room, it
Yes.
would melt and its temperature would increase,
Okay.
because things, they tend to move towards equilibrium.
Oh, so it's
things
physics.
things, they tend to move towards equilibrium. So anything which has a higher temperature than its surrounding, it would pass off, it
Yes.
would share some of its higher temperature with the surrounding, until the temperature of the surrounding and the substance itself, it becomes equal.
Yes.
And something which is cooler than the surrounding, it would draw in heat from the surroundings until the surrounding and this
Uh-huh.
thing, it's equal. When
Yes.
somebody has got like cold cheeks, you put your hot
Mhm.
hands on their cheeks. Why? Because you're trying to
Mhm.
pass off the heat from your hands to their cheeks.
Oh. Wait, okay, what's the science? You know how some people say if
Hmm,
you rub your hands together, it creates like heat energy, so you should do
friction.
that when you're cold?
Friction.
Oh, it creates heat?
It does. Friction creates heat.
Okay. So is that why people rub their hands
Yep,
like when they're cold?
exactly.
Okay. I
All
have a
right.
question.
Sure.
Are you like genuinely interested in physics? Or were you forced?
Does it look like it?
I don't know. You're genuinely interested?
um, yes, maybe. I'm generally interested in teaching whatever I teach.
Okay. You were
So,
never forced into this?
into teaching, no. So I was pursuing a career in chartered accountancy, and
Oh.
uh, I was at, I don't know if you know about the audit firms or not. I was at PwC. I worked over there for
Hmm.
4.5 years. But uh, my plan when I left PwC was that I'd work in the industry for some time and then eventually I'll
Hmm.
become a teacher, because that is what I want to be in the long term. But
Yeah.
the way things turned out, I started teaching with a before any other career, and so I'm continuing with it.
Wow. Mashallah. Very successful. Very successful.
Okay. uh, if you could look at this conceptual challenge, which
Hmm.
is on which page?
300.
It is it 300? Yes, 300, please. If you
Yeah.
could read these questions and explain these to me.
Okay. Um, if two cups of hot chocolate, one at 50 degrees Celsius and the other at 60, are poured together in a large container, will the final temperature of the batch be A less than 50, B between 50 and 60, or C greater than 60? I know.
Hmm.
Okay, wait. Let me process.
They lose some of their energy to the surroundings, or
Oh,
if they gain some energy from the surroundings, external energy, then this
yeah.
temperature, it could be above 60 or below 50.
So like if the hot water cools down a little bit, that's
The hot water would cool down a little bit. This is just hot
uh,
water. Let's say hot water and cold water. I mean,
mhm.
hot chocolate and whatever. Okay, so hot water and cold water. One is at 50
Mhm.
degrees centigrade, the other is at 60 degrees centigrade. We put them
Okay.
together. Uh,
Mhm.
Eventually, the temperature would settle in between 50 and
Mhm.
60.
Yeah.
That is what would happen if they are neither passing off any of their energy to the surroundings. It's just exchange of energy between these two different temperatures of waters.
Okay.
They are just exchanging energy with each other, right? They're not letting any energy escape from the container outside, nor are they absorbing any energy from outside the container. Did you get this thing?
Yes.
Okay, in normal circumstances, when we put in our daily lives, energy is not conserved. So for example,
Mm-hmm.
if I mix water of two different temperatures in one cup, they would pass off some of their energy to the surroundings. In labs,
Mm-hmm.
when we are doing the experiments, we try to contain this thing,
Mm-hmm.
that neither any external energy it comes in and disturbs our experiment, nor any energy it escapes from the environment in which we are performing the experiment. If that is the
Mm-hmm.
case, if we are if for example the energy is total energy is conserved, right, then the temperature would be
Mm-hmm.
between 50 and 60. But if
Yeah.
energy is not conserved, and what does it mean that energy is not conserved? Either some external energy is coming into this experiment, or this experiment is
Okay.
losing some of its energy to the outside.
Yes.
In that case, energy won't be conserved. You speak in that funny accent, so I don't know if you're actually getting the concept or if you just want me to move on.
Funny accent.
I mean, your yes, I can hear a hint of smile behind it. I don't know if it's like suggesting that just get on with this thing. Anyhow, question two, please.
Okay. A cup of hot tea is poured from a teapot and a swimming pool is filled with cold water. Which one has a higher total internal energy? Which has a higher average kinetic energy? Explain. Please pour. Okay. So I'm not sure what the answer is.
Hmm.
Total internal energy.
What was the difference between total energy, total internal energy, and the kinetic energy? Kinetic energy is just a part of total internal energy, right?
Hmm.
In total
Yeah.
internal energy, there was both kinetic and potential energy.
Hmm.
So now, which would have higher internal energy and which would have higher kinetic energy?
Well,
Hmm.
um, can you explain?
Give it a go. Eventually, I will explain, but at least give it a go.
Okay. Mm. So, total internal energy is kinetic energy and potential energy together, right?
Hmm.
Okay. So, if hot tea is being poured, isn't that like potential energy?
Let's say
Like,
it's not being poured somewhere. There is just
okay.
hot tea in a container,
Okay.
and there is a hot tea in teapot, and there is
Hmm.
water in swimming pool.
Hmm.
Which would have higher internal energy and which would have higher kinetic energy?
Okay. I think the swimming pool has higher kinetic energy because it's bigger. So,
Hmm.
there's more particles that move.
All right. And what about tea?
And tea, it is hot, but
When is something more hot?
when is something more hot?
Hmm.
When
Which energy has to be higher for the thing to be hot? Internal energy or kinetic energy?
uh, kinetic.
Kinetic energy. So
Oh,
if tea is more hot than water in the swimming pool, then tea has got more kinetic energy.
oh, okay.
Number one. And what about internal energy? Since tea is in a small teapot, it's a very
Mm-hmm.
small quantity of tea. And
Mm-hmm.
water in the swimming pool as compared to teapot is a lot, is greater in volume and
Oh, I
quantity.
mixed my answer. I
So,
meant the total internal energy is higher in the pool than the tea. My answer
yeah,
was
yeah.
mixed.
Correct. Okay.
Okay.
Uh, this then the next thing is, in order to measure temperature, what do we do?
Use thermometer.
Okay. We the device that we use to measure temperature is called thermometer. Usually, what we are using to measure the body temperature
Mhm.
is mercury thermometer. Okay. So in
Okay.
thermometer, what's the principle? That we have got a liquid within the glass,
Mm-hmm.
within the glass tube, and it has got a bulb. The bulb is
Mm-hmm.
sensitive to the change in temperature.
Yes.
There is a reason that the bulb is where we put, I mean, in contact with our skin, where we want to measure the
Mm-hmm.
temperature of, from our skin. One thing. The second
Mm-hmm.
thing in that the thermometer, it shows certain readings. Okay, why does it? I
Okay.
mean, how does it work? Is when that bulb is put in contact with the body passes on the
Mm-hmm.
heat to the bulb. The bulb passes on that
Okay.
heat to the liquid inside it, which is mercury, and the mercury expands.
Mm-hmm. Yes.
Okay,
We
so
we did this. We did an experiment in class. I
hmm,
think
hmm,
the mercury with the thermometer, because I don't remember. I think the water with
hmm,
water. There was one cold one and there was one hot one.
hmm.
So not sure.
Okay, okay. So how do we, for example, if I've got an unmarked thermometer, how do I
Okay.
put marks on it? This is called calibrating thermometer. Putting marks on some.
Calibrating.
Hmm. So let me write over here.
How do scientists do that?
I'm
How
about to
do
tell
they
you.
know?
About to become a scientist of thermometers, calibrating. The thing that you need to write down, however, before you become the
Mhm.
scientist is calibrating thermometers.
Are you a scientist?
Pseudoscientist is a better term.
So you're not a scientist. Are you?
Um, I'd like to think I'm one, but I'm not.
Oh, okay.
Define scientist,
I don't even know actually what is a scientist.
then I'm a
I mean, I know,
scientist.
but I don't know what's considered like a scientist.
If you don't know what a scientist is, then I am a scientist.
Okay.
Okay, okay. Now, how do we do this calibration of thermometers? We put
Mhm.
this thermometer inside something,
Yes.
inside the substance at
Hmm.
which has a temperature of, which has a known temperature of 0 degrees centigrade.
Okay.
Okay, the mercury inside the thermometer, it would contract, and it
Hmm.
would reach a point where it does not contract anymore. So
Hmm.
if this is the thermometer, and initially mercury was over here, excuse my bad drawing, but uh, initially it was over here, and then when I put it in cold
Mhm.
water, it reached this particular mark.
Okay.
Okay, so this is 0 degrees centigrade.
Hmm.
Okay, then I put the same mercury thermometer in a liquid of known temperature of 50
Hmm.
degrees centigrade. So it would expand, and it expanded up till this point.
Okay.
Okay, so the other thing I have to be careful about, why do we use mercury, why not any other material? For example, we have got alcohol thermometers, we have got mercury thermometers, why don't we use any
Hmm.
other substance? The thing is that for whatever range we are trying to calculate the temperature, for example, here we are trying to calculate between 0 degrees and 50 degrees centigrade, it
Hmm.
has to be that the expansion volume
Hmm.
with regards to temperature, it has to increase uniformly, it has to be a straight line.
Hmm.
It can't be that for some temperature range it rises rapidly, then for some it does not rise as rapidly.
Okay.
Okay, or if it's like a curve, we can't have something like that. So we have to
Hmm.
use a liquid which changes, whose change
Why
in
can't we
volume.
have a curve?
Okay, the reason we can't have a curve, then we won't be able to calibrate the thermometer. It would be difficult to calibrate the thermometer. So from
Oh, okay.
this temperature to this, how, what I would do next in this mercury thermometer is that from here to here it's 50. I could divide
Mhm.
it with 50. This whole distance, for example, this distance was 50 centimeters. For
Uh-huh.
example, I can say that each centimeter represents a change of 1 degree centigrade.
Mhm.
But if this change is not uniform, if it is in the form of curve, then it's
Mm-hmm.
difficult to predict. For example, if the temperature if it increases from 10 to 20,
Okay.
it's different change of volume, and when it
Mm-hmm.
increases from 20 to 30, it is a different change of volume.
Oh.
So each change of volume, for each same change in temperature, same blocks of change in temperature would be
Mm-hmm.
represented by different change in volume
Okay.
if it's a curve. So we have to choose a material
Uh-huh.
for which it is constant. This change in volume to change in temperature is constant for
Mm-hmm.
the range for which I'm trying to calculate the
Okay.
temperatures.
So
Did you get?
that's why mercury is used.
That's why mercury is used. That's why alcohol is used.
Okay.
These are two most commonly used ones. The other thing about mercury and alcohol is when you do lab experiments, you usually use alcohol thermometers.
Mm-hmm.
Why? Why not mercury thermometers over there?
Because
Okay, when you're trying to measure, if for example you feel feverish, you use the mercury thermometer. How long does it take the thermometer to give you reading?
a few seconds.
A minute to 2 minutes.
Okay.
You put the thermometer in your mouth for a minute or two.
Oh, okay. Yeah.
Okay, so that is the time mercury takes to adjust to the temperature change, right?
Oh, okay.
Okay, so if you put mercury, I mean that thermometer in your mouth,
Mm-hmm.
and it takes 1 minute to give you reading.
Mm-hmm.
If I'm doing a lab experiment, for example, I'm heating something,
Yeah.
and by the time I note reading on the thermometer, it's showing me a reading which was 1 minute ago,
Oh.
which was the temperature 1 minute ago. So in lab, I need a liquid in the thermometer which responds more rapidly, more quickly to the change in
Mhm.
temperature.
So alcohol responds
More quickly
within.
for and that
Okay.
is why we don't use alcohol thermometers to measure our body temperature, because by the time you take it out of your mouth and try to read the reading, the temperature, I mean, the reading would have already changed.
Okay.
It responds that quickly. So it's useful in lab but not as useful
Mm-hmm.
for measuring the body temperatures, and that is the
Mm-hmm.
reason mercury thermometer is useful for measuring temperatures and not as useful as in labs.
So in regular thermometers, there's mercury.
Hmm. Hmm.
It takes a minute.
It takes a minute to 2 minutes. Yes,
I
depend.
think I've been I
Hmm.
think I've been using it wrong then. I do it for like 1 second, I think. So
I mean, there are digital ones which give you readings very quickly, but even
okay.
they take a few seconds at least, from what I know.
Okay.
But personally, the ones that I've got at my home, they are the mercury thermometers, and they take up to 2 minutes to give you the reading.
Oh. Okay.
Okay. Also, you have to reduce the temperature to a certain level before you start taking the reading on the thermometer.
Mm-hmm.
I don't know if you did that or not. Did you get this thing of how do we calibrate the thermometers? We
Yes.
first of all, we need to know that there are different liquids in the thermometer,
Mm-hmm.
and we are using the concept of thermal expansion, that these liquids, they expand or contract when they are exposed to cold or hot settings.
Mm-hmm.
One thing. The next thing is that we are looking for a liquid which has got
Mm-hmm.
a linear change of volume to temperature ratio. It's a straight
Okay.
line, the change in volume to change in temperature. So
Mm-hmm.
we set it for the lowest most reading. Let's say we want to see it for 0 degrees centigrade, which is the melting or freezing point of water, and we want to
Mm-hmm.
check it for 50 degrees centigrade. All
Yeah.
right. So from between 50 to 0 degrees centigrade, the change in volume to change in temperature ratio should be constant. I don't know
Okay.
how good you were at math, but uh, this is called this is called uh, the gradient is constant. Do you understand the gradient being constant?
Yeah, I took this, but
So change in volume to
uh,
change in temperature. I mean,
mhm.
gradient is calculated delta y by delta x. So
Okay.
throughout a straight line, this delta y by delta x is same.
Hmm.
For straight line, gradient throughout the line stays the same. the
It's
slope
constant.
the slope of the straight line is constant, or gradient of the straight line is constant. Okay,
Okay.
so we are looking for a material which has a constant relationship or a straight line
Hmm.
graph for change in volume to change in temperature ratio. So we
Okay.
can use that. We have the highest most reading, we have the lowest most reading, and we can
Hmm.
divide the distance between them according to change in temperature. Okay,
Okay.
if this distance were, for example, we took the easy example where we had 50 centimeters representing 50 degrees centigrade, we could have
Hmm.
something different as well. So for example, for 50 degrees centigrade, we could have a change of, let's say, 16 centimeters as well. So what would we do then? We'll divide both sides with 50. So I
Okay.
get 1 degree centigrade is represented by 16 over 50 cm.
Hmm.
So every 15 over 60 cm, I can put a 1 degree mark.
Yes.
Okay, so this is how
Hmm.
we calibrate the temperatures. We'll
Okay.
take it from here in the next class. We'll resume
Hmm.
it from here, inshallah. uh,
Okay.
in the meanwhile, in the